Lawrence Livermore National Laboratory. His research focuses on integrating field monitoring techniques with large-scale computing to improve the understanding of complex geologic systems. The areas of interest for his research include geologic carbon sequestration, Livermore National Laboratory. His research focuses on integrating. I'm sorry, I was able to hear myself. Okay, so the areas of his research include geologic carbon sequestration, geologic hydrogen storage, and induced seismicity. Dr. White holds a BSc in Civil and Environmental Engineering from Princeton University and a MS and PhD in Civil and Environmental Engineering from Stanford University. So thanks again, Josh, for taking the time to speak with us today, and the floor is all yours.
Great. Chandra, everyone, thanks again. It's a real honor to be invited to speak here this morning. Let me just try to share my screen again. Can you see my slides in presenter mode?
Yes, perfectly.
Yeah. Perfect. Yeah. Great. Well, this is a really wonderful opportunity. With the pandemic, it's been so difficult to see colleagues in person at conferences and seminars and so forth. So this is a really nice opportunity to connect once again with old colleagues and maybe future colleagues. So thanks again. So like Chandra said, I'm going to talk about computational geomechanics, and in particular, thinking about how we can begin to use very large-scale computers that are coming online, well, that are available today, and even larger systems that are coming online in the next 5 to 10 years. So I do a lot of work in various areas of the subsurface. Work on geologic carbon storage, hydrogen storage, some traditional oil and gas activities. And so we spend a lot of time using simulations to actually understand the behavior of these systems. So as one example, this blue sort of blobby figure you're looking at right now. So this is actually a reservoir simulation for a potential CO2 storage system in the Gulf of Mexico. And so it's a highly faulted system. So each of these offsets you can see here is actually a fault in the subsurface. The injection location is where this kind of red hotspot is. And we're actually looking at the pressure migration away from the well and how that pressure plume may interact with those faults. And as you can imagine, hydromechanical interactions, the interaction of fluid, pressure, and the solid mechanics plays a really important role in the performance of many subsurface systems and in a variety of ways. So here I'm showing a schematic cartoon of a carbon capture and storage system, but many of these same processes apply to other subsurface activities. So here you can see we have a point source of CO2. This might be a power plant or some industrial process that produces a lot of carbon dioxide. We transport it via pipeline to an injection well and then inject it deep into the subsurface. For CO2 storage, we often inject it into a salty aquifer, a deep brine aquifer, often more than 1 kilometer deep, often 2 kilometers deep in the subsurface. And as we inject that CO2, you can imagine there's a plume of CO2 that's moving away from the well. But since we're, the pore space is already filled with one fluid and we're introducing another fluid, we're building up fluid pressure in the water itself. And so we have this pressure plume that migrates away from the well as well. This is a rock. It's a porous skeleton. So as we pressurize that rock, we get dilation of the rock. And then we can also have effects, for example, in the subsurface, we often have faults and fractures. And so that fluid pressure can interact with those faults, interact with those fractures, cause opening of fractures, shear on faults, all sorts of mechanical activities. And so when we design these systems, we have to have a really good understanding of things like stress-dependent permeability, the possibility of hydraulic fracturing or hydraulic shearing, the potential for fault reactivation, even the potential for induced seismicity. And then more recently, there's been a move in many operations to actually using direct deformation monitoring as a way to actually monitor the subsurface. So measuring, for example, the movement of the ground surface, we can begin to kind of infer what the pressure behavior looks like in the subsurface. Or, for example, deploying fiber optic cables along a well, we can actually directly measure strain along that well and use that to inform our subsurface operations. So to give you a very practical illustration of this, this is the Insala CCS project. So this is one of the largest onshore carbon capture and storage projects that's been operated to date. It took place between 2008 and 2011 in central Algeria. So it's an oil and gas field where the gas that they were producing had a very high CO2 content. And so they would remove the CO2 before shipping the natural gas to Europe and other consumers. And they would re-inject that CO2 through several wells. And in particular, looking at a plan view of the site, they're producing gas from this kind of gray region. So these black dots, these are all wells that they're producing gas from. But then they would re-inject the CO2 in wells 501, 502, and 503. And these are long reach horizontal wells. So they go down vertically and then they deviate horizontally to attempt to provide as much access to pore space as possible for that injection operation. Interestingly, what they did though is they used a satellite-based deformation monitoring technique called INSAR, interferometric synthetic aperture radar, to actually measure movement at the ground surface. So they're injecting CO2 at about 2 kilometers depth, but they're using radar shots from a satellite to actually monitor the movement of the ground surface. And so that's what this figure on the right is showing. So this is labeled as range change. This is basically the movement towards the satellite, but you can think of it more or less as vertical uplift. And so immediately above the injectors, so KB501, KB502, and KB503, you can see that there's this very clear signature, this sort of elliptical uplift of about 2.5 millimeters. Due to, again, that pressurization of the reservoir, the inflation of the reservoir, and then this far field deformation that's propagating all the way to the surface. Now, the actual deformations are quite small, 2.5 centimeters spread over several kilometers. No one at the ground surface would actually be able to detect. A human wouldn't notice these sorts of deformations, but they were very useful as an additional piece of information for attempting to constrain how the pressure and fluids were migrating in the subsurface. So, for example, the reservoir itself is highly fractured. And so we know that there should have been a pretty strong stress-dependent permeability effect. And you can actually see that you see how these plumes are kind of elliptical and they're oriented in this particular sort of northwest southeast direction. That corresponds pretty well with our understanding of the in situ stress. And so we would expect actually preferential flow in that direction, and that would lead to preferential deformation. So this was sort of a confirmation that was happening. Midway through the project though, they noticed that the behavior of the deformation above KB502 was quite unusual. It had this kind of horseshoe pattern with a trough in the middle. And this prompted a lot of questions. What was going at on a KB502? Why was the injection seemingly so different than at KB501? And the end result was there was some thought that this may actually be because they hydraulically fractured near that KB502 well. And if that was the case, you would expect with a large vertical fracture to actually create an uplift pattern that would look like this. They went back and reanalyzed well test data and 4D seismic data and confirmed that they had actually inadvertently hydraulically fractured because they were injecting at such high pressures. And so even though this is a very indirect monitoring technique, it was actually extremely useful for identifying a problem with the operation and helping to guide some of the interpretation of what was going on in the subsurface. Most of my work is focused on the deep subsurface, sort of energy-related applications, but I am also interested in the shallow subsurface. I continue to be interested in a lot of sort of geotechnical hazards, in particular rainfall-triggered landslides. And so these follow very similar processes. You know, as rainfall seeps into the subsurface, it changes the subsurface pore fluid pressure conditions. That changes the effective stress conditions that the soil is feeling and can eventually lead to failures. And so, for example, this is a very large landslide failure in Peru from 2018. And again, computational tools can be really helpful here. You know, understanding how the fluid pressure in the subsurface may change. For example, here we're looking at a landslide simulation, you know, looking at a slope failure simulation. We're looking at a cross-section, so a vertical cross-section where we have this very thin layer of soil basically on top of bedrock. So we don't model the bedrock. And we're modeling the pore fluid pressure and how that evolves with rainfall and infiltration, and also how the soil itself might evolve, the plastic strain of the soil, and then the eventual formation of these slip surfaces, which would correspond to these failure surfaces. Here you're seeing these scarps, as we call them. Okay, so hopefully I've motivated that hydromechanics and geomechanics and flow and transport processes are tightly coupled. And hopefully it's clear that we want to be able to model these in a really effective way. And so the question is, how can we use computers? And more importantly, how can we use very large computers? I think it's interesting to look back, though, on the history of computing. So just as a fun snapshot, this is a photograph of Lawrence Livermore National Laboratory's first computer from 1953. So this was a UNIVAC 1. I believe they called it the toaster oven because it looks a little bit like a toaster oven. It was a room-sized computer that could achieve 2,000 operations per second. Many of you are probably sitting close, well, you're all sitting in front of a computer. Many of you are probably sitting close to a cell phone that has much more computing capacity than this room-sized computer ever did. But if we look at today, this is the top 500 list. So if you're not familiar with the top 500, this is a list of the most powerful supercomputers in the world. And the list is constantly updated because it changes every few months. So I have a snapshot here from June of 2020. There's probably a more recent list coming out fairly soon. So in terms of the computers, so I work at Lawrence Livermore Lab, and so we currently own the #3 most powerful supercomputer in the world, our Sierra system, which looks like this. The most powerful system in the world is actually in Japan at their supercomputing center. But you can see that all of these systems, these are really very large national government laboratory systems. You know, these are government investments trying to put out, you know, the largest supercomputers in the world. And so you see currently the United States, China, Japan kind of topping the top 5 here. What's very interesting, though, to me is if you look just a little bit further down the list, that actually the #6 supercomputing system in the world, the 6th most powerful computer in the world, is actually owned by an oil and gas company. It's owned by Eni from Italy. Similarly, the number 15 and 49 systems are owned by Total, now Total Energies, the French oil and gas company. Number 19 is Eni again. Then 56 is Petrobras. Number 62 is Petroleum Geosciences, PGS. You know, the energy sector actually consumes a huge amount of computing cycles. This is largely driven by seismic imaging. That's a very computing intensive process, but it's also being used for reservoir simulation and so forth. I think this probably surprises people. Like, for example, if you want to look at the tech sector, that might be the natural place. You might think, oh yeah, Google, Facebook, Amazon, these sorts of big companies, they must be using large supercomputing. It is true they are, but in a very different way. They're largely focused on data sciences, machine learning, and stuff. And so you actually have to go quite far down the list to Facebook at number 76 before you really see the tech industry on these supercomputing lists. The other thing that's interesting to note is that these very large systems, for example, for much of the past decade and before, we've largely relied on CPU-based systems. But now the latest generation of systems, and certainly for the next probably 5 years at least, much of the computing horsepower of these systems is coming from graphics processing units, from GPUs. The same thing is true in your laptops. You're saying, your laptop probably has a GPU card, or in the next few years, certainly will have a combination of CPU and GPU chips on your system. This is really great. It provides the potential for orders of magnitude gain in performance. Unfortunately, it substantially complicates the programming that we need to do to take advantage of these systems. You cannot take a traditional kind of high performance computing code that ran really well on a CPU 5 years ago and just port it onto this Sierra system and expect it to work well. There are sort of fundamental changes both in our algorithms and then in actually the software that we design to implement those algorithms. And so that's a major challenge for us in the computational geomechanics and reservoir simulation space. Currently, just to give you an image, we're here in sort of 2020, 2021. The largest systems in the world are in this hundreds of petaflops range. But we're about to cross into what we call the exascale era, achieving 1 exaflop and beyond. So in the United States, we have a very clear timeline for the delivery of the next generation of supercomputers. This year, they're currently deploying at Argonne the first exaflop system. Then same thing's going to happen with this frontier system at Oak Ridge. And then in 2023, where I work, Lawrence Livermore, we're getting our El Capitan system, which should hit our peak performance of 2 exaflops. So really just amazing amounts of power. But unfortunately, I can't just give you a huge supercomputer and we can't just automatically run very large models on it. The process of getting from our partial differential equations and our constraint equations to an actual simulation on a very large computer involves many, many steps. And there are many, many sort of bottlenecks and research that needs to be done to enable this. So in a typical reservoir simulation workflow, we start from characterization data. We then have to construct sort of a model, a geomodel of our system. We then need to make decisions about the governing physics. What is the appropriate physics to include in our systems? And there's lots of research activity about this. Then we often have to do constitutive modeling. What are appropriate models for rocks and fractures and fluids in the subsurface and how they mix. Lots of research there. Then we need to make a decision how we actually discretize this governing physics. Do we use finite element schemes, finite volume schemes? Those are really great for a broad suite of problems, but there are many problems for which those are not well suited, particularly when you start talking about fractures and faults and polyhedral meshes and more complicated discretization challenges. Then, once we have a discretized set of equations, ultimately, we then usually need to invoke a nonlinear solver and a linear solver. And this can be a major bottleneck. And this is actually going to be the one I'm going to talk about today, just to pick out one particular research area where we focus. Then once you've got all this, you have to actually put all these algorithms into software. So we need certain programming models. And then we need to actually run them in a way that intelligently uses the infrastructure. So uses a CPU, uses the GPU, understands how memory gets moved around that system, and avoids parallel communication bottlenecks and memory bottlenecks and so forth. And then eventually, we usually don't care about running one simulation. We usually want to run ensembles of simulations to do things like data assimilation, uncertainty quantification, risk assessment, and then ultimately we get to some decision. So it's a very complicated pathway. It's great though, because that means there's lots of avenues for really impactful research. I think many people in the room are contributing to components of these within that broader picture, and that's really great. So to maybe fix ideas, this is one model that we frequently use for modeling subsurface fluid injection operations. It's a slightly simplified version of the models we typically use in practice, but I didn't want to give the full complexity. That's probably too much. This is complicated enough. This is multi-phase pore mechanics. So imagine that we have a solid skeleton, the rock skeleton, which is deforming, okay? And so that deformation is quantified by a displacement vector U. We then have two fluids in the pore space. Imagine a wetting phase like water and a non-wetting phase like oil, okay? And the volume fraction of those two phases is quantified by the saturation S. And then we have a fluid pressure P, so the pressure in the fluid. And for the moment, we're going to ignore capillary pressure. So we can actually assume that the fluid pressure in the water and in the oil is actually equal. So there's just one pressure as opposed to two pressures. Then we typically need to solve a linear momentum balance, which relates quantities like the effective stress in the rock, the pore fluid pressure, BO's coefficient, the density of the mixture, and body forces due to gravity, And so this is our linear momentum balance. We then have two mass balance equations, which are really tracking the mass of fluid moving in and out of a volume, but it needs to account for the deformation of the rock because the porosity is changing. And so we're looking at time rate of changes in porosity and density and saturation. V here is the fluid velocity, and Q is a source. And then we close these governing equations with various constitutive models. We have a stress-strain relationship, maybe linear elasticity or some poroelastic model. We have Darcy's law, which relates the fluid velocity to the fluid pressure gradients and gravity potential gradients through a permeability term. And then we have a constitutive equation for the porosity itself, which relates changes in the porosity to the volumetric strain, as well as to the fluid pressure being experienced in that pore space. So if there are questions, I'd be happy to talk about these governing equations in more detail. They're really not central. The key idea I'd like to convey, though, is that we have three fields: displacement, saturation, and pressure. They're tightly coupled to each other through three governing equations: this momentum balance equation, mass balance equation, and oil mass balance equation. And we want to solve for all of these simultaneously in some sort of numerical algorithm. And so typically when we run a simulation, we follow a structure, that's usually looks like this. Almost any reservoir simulator or sort of nonlinear simulator looks like this, where we do some pre-processing, we build a mesh. We then have a time-dependent problem, so we're doing a time loop. We then have a series of nonlinear equations, and so we need to solve those using some sort of nonlinear solver algorithm. More often than not, that's Newton's method, though it doesn't necessarily need to be. And so what we do is we assemble actually a linearized version of the problem, basically a very large algebraic system, AX equals B, a big matrix system that we need to solve. So we assemble that system. And then we use a series of solutions of those matrices to kind of advance the solution to nonlinear convergence and then forward in time. Okay. And the thing I want to convey is that for many of these systems where we use implicit time stepping and we need to solve these large linear systems, this linear solve is actually the dominant computational cost. It will often take 80%, 90% of the total simulation time. And so this is where we spend a lot of our time really trying to optimize performance, because if we can drive this cost down, we drive down the whole simulation cost. And if we can't do this well, it immediately puts an upper limit on the size of problems that we can actually solve. The challenge, though, is that we have here, for example, like I said, we're solving 3 governing equations for 3 unknown fields. And so I'm quantifying this. Imagine I have a linear system. So this is A, X equals B. The right-hand side has our residual quantities. So this is the residual for the momentum balance, residual for the wetting phase mass balance, and the residual for the oil phase mass balance. Our solution vector has a long list of displacements, saturation and pressure unknowns at various points on our computational grid. And then we have this very large block structured linear system, which quantifies all the couplings between displacements, saturations, and pressures. And we need a solver that can actually handle this very complicated algebraic structure. And so maybe to give you a concrete example, this is a common benchmark problem that we use for poroelasticity. It's called Cryosphere. Imagine I actually have a spherical sponge filled with fluid. I load it from the outside with some load, and I measure the pore fluid pressure that actually builds up at the center of the domain. Okay, and it's interesting. So looking at the pressure here, non-dimensionalized versus time, at T0, we start loading it, and you can see that we actually build up fluid pressure in the center of the domain. But then that fluid is able to leak outside through the outer surface of the sphere. And so over time, we have a decline in fluid pressure. And since it's a spherical geometry, it has a nice analytical solution in radial coordinates. And so we can use this to verify that our implementation is correct and so forth. But here, what we're going to do is we're actually going to model it as a 3D domain. And so we discretize an eighth of a sphere because we can exploit symmetry boundary conditions with a particular discretization scheme. We model both the fluid pressure and the deformation of this sphere, and we modeled it forward in time. And we can do quite a good job matching the analytical solution as we would expect. The thing I want to convey to you, though, is that having a really good, what we call preconditioner, a really good linear solver, is essential to scalable performance. Unfortunately, these systems quickly get too large for direct solvers, what we call direct solvers, to solve them. And so we often use what are called iterative solvers, Krylov-based methods to solve these systems. If you've heard of things like conjugate gradients or GMRes, generalized minimum residual, or by CG stab, by conjugate gradient stabilized. These are iterative methods for solving large linear systems. But the performance of those methods really depends on what we call a preconditioner. Basically, the convergence of these methods depends on the eigenvalues and the eigenvalue and eigenvector distribution in our matrix. Unfortunately, naively, when we assemble these systems, they have a really terrible eigenvalue distribution. They're really poorly conditioned. And so what we do is we introduce an operation, what we call preconditioning, to attempt to improve this eigen decomposition, improve sort of the clustering of these eigenvalues in such a way that we can really accelerate performance. Okay, so that's kind of like a complicated mathematical explanation. What does that mean in practice? In practice, if I take a problem at one mesh refinement level, okay, and I use a particular solver, it will take a certain number of iterations to converge. And so you can see here, I've done this for 2 cases, one with what we call a naive preconditioner, and one with which is a mathematically informed, quite intelligent approach to this particular problem. And for small problems, you can see we converge in about 40 iterations. Great, we declare victory, that's nice. But you can see if I refine the mesh and try to solve a larger problem, if this naive preconditioner, all of a sudden it's taking a little bit more iterations. And then if I refine the mesh again, it's taking a lot more iterations. And if I keep going to very, very large problem sizes, you can see that there's no way I can achieve scalability. I can't continue to solve larger and larger problems because the work I need to do is growing with time, and that's not good. Whereas using some intelligent approaches, and here with this thing we call a fixed stress preconditioner, you can see that as we refine the mesh, we're taking essentially a constant number of iterations. And that's sort of the first ingredient to scalability. That says that, even though we're solving larger and larger problems, we're keeping a lid on the amount of work we need to do. And that holds out some hope for solving very, very large problems. And so that's a lot of the mathematical work and computer science work and software development work that we do around linear solvers is really trying to make sure that as we solve larger and larger systems, we can really kind of keep a lid on the amount of work that we're doing. So now this gets very complicated, how we actually do that. And there's no time really today to talk about it. I'll say we do a lot of work on algebraic multigrid methods. These are very efficient methods for solving certain classes of problems. Unfortunately, traditional algebraic multigrid methods are not well suited to multi-physics problems, where I have strong coupling between a variety of fields. Again, like I said, I have a coupling between displacements U, saturations S, and pore pressures P. And we need to inform our linear solver with respect to all of these couplings. And so we developed a particular technique, which we call multigrid reduction. So it's a flavor of algebraic multigrid, but suited to systems of partial differential equations. It relies first on building a hierarchy of problems where at the lowest level, you can imagine that we have the fully coupled problem, U, S, and P. We create a coarsened version of the problem where it really only depends on saturations and pressures. And then we create an even coarser version of the problem where we've eliminated the displacements and saturations from the problem and only have the pore fluid pressure. So we create this sort of hierarchy. And then within each of these levels, we build another level of hierarchy using sort of multi-grid techniques. But the point is that we intelligently think about how these couplings are impacting the algebraic structure of this linear system, and we try to inform our solver. And in doing so, we can get quite good performance. And so just to show you this, a real problem maybe. So this is a more complicated multi-phase problem. So this is multi-phase pore mechanics. Imagine we have a domain with what we say is a high permeability channel in gray. So high permeability rock, which winds its way in sort of a staircase fashion like this. And this is obviously no geology actually looks like this. This is deliberately deliberately constructed to really challenge the linear solver to make the problem as difficult as possible for a linear solver to ensure that we have very strong coupling between all the fields and so forth. Anyway, so what we do is we inject a fluid here through a well in the top. And you can see this fluid, there's a saturation plume that migrates its way around to a producer well that is actually at the bottom here. And so we're modeling this fluid saturation plume migrating. We're also tracking the fluid pressure as it evolves. So we build up high pressure near the injector and low pressure near the producer. And then we also track the displacement of the sponge. This whole thing is displacing. And so you can see that the upper surface is uplifting because of this increase in fluid pressure. And then there's a little bit of contraction at the bottom. Okay, so we solved this problem, and we do what we call a weak scaling study. And so the idea is I start with a problem with a certain size, which is 680,000 degrees of freedom. So I have a matrix that has 680,000 rows, and I solve it on 2 cores of one of our parallel machines. And then what we do is we refine the mesh. So we get a problem that's 8 times as large with 5 million degrees of freedom. But we throw 8 times as many cores as it. So we're saying we're increasing the problem size, but we're proportionally increasing the resources we have to solve that. And then we keep going until we have 1,000 processors and a problem, a matrix with 337 million rows. Okay. And again, coming back to that question, how does our linear solver, what does the iteration count look like? Does it just explode, or are we able to keep kind of a lid on that? And in this case, we are. We start for the smallest problem size, we take 10 iterations to converge. for this huge, massive problem with 337 million degrees of freedom, we take 16, which is really great. In terms of the actual time to solve the problem, we do see some increase in time, and we have actually improved on this. This problem takes 3 times as long to solve as this problem. But keep in mind that the problem is actually 500 times as large. So we have quite efficiently used this very large resource, this 1,000 processors, to solve a very large multi-phase flow problem. We've been applying this same solver to other physics. So for example, we do some work on hydraulic fracturing. So this is a similar problem where we have deformations of a rock and fluid pressure. The challenge here, though, is that actually the rock can break. So we have fractures that can propagate. But at any given time step of that simulation, we need to solve for kind of the equilibrium configuration. So we need to understand how fractures are opening and what's the displacement field that leads to sort of a stress equilibrium. And so the algebraic structure is similar, but you can see the connection to the previous problem that I talked about. So here we're looking at a very large domain. There's a horizontal well that's passing through it. And then there's a variety of perforations. These are places where we penetrate the well, and we deliberately inject at very high pressure to try to sort of propagate the fractures. And then each one of these, you probably can't see them so well, but each of these kind of green, blue things is actually a fracture that's propagating away from the well. There's this heterogeneous stress field, and so they're kind of lumpy, and then there's all these stress shadowing effects, and so it creates like quite a complicated structure. If you look at a side view of one of these fractures, for example, let's see, at 308 seconds, the fracture looks like this, and then a little bit later, it looks like this, and then a little bit later, it looks like this. For the experts in the field, this simulation was run without leak off. And so as a result, the timescale here is a little off from what you would expect in a real field case where you have leak off, which has a really important impact on the timescale dynamics. We were testing the solver, and so we wanted to focus on the simpler problem of just fluid pressure in the fracture and the deformation of the solid matrix. But we do a similar sort of thing. So we have a problem size. Here we start with a problem size of 21 million degrees of freedom on 216 cores. But eventually we refine the mesh out to a problem size of 171 million degrees of freedom on 1,700 cores. And you can see that the number of iterations is essentially constant. There's some fluctuation, but really there's a cap on the number of iterations here. And actually the time per solve, we're able to solve this 171 million degree of freedom problem in less than 10 seconds for a particular Newton solve within a much larger time dependent simulation. Obviously, the whole simulation takes much longer than 10 seconds. Okay, so time is getting on. I'd just like to say that we focus heavily on community software and open source software. So everything I've showed you today, the linear solvers, these very scalable multi-grid solvers for systems of PDEs is all available via Hyper, which is a linear algebra solver package developed at Livermore. And the simulation capabilities that I've shown are all available via our sort of reservoir simulation and geomechanics code, which we call GeoX, which is really around scalable multi-physics simulation. And this is open source, available at geox.org. And you're welcome to download it and try and contribute to these projects if you're interested. Yeah, so maybe to quickly wrap up, I focused a lot on the linear solver. I think it's an area that people often forget about. I certainly know when I was in grad school, I spent a lot of time, my PhD was really around governing physics and discretization. But I always used a direct solver. And so I was always solving these like 2D problems, 2D problems, because I couldn't solve anything bigger. And it's really frustrating because real life rarely looks 2D. Sometimes it does, but rarely it looks 2D. We want to run 3D problems, lots of heterogeneity, fine detailed structure. And in order to do that, we need really scalable linear solvers and nonlinear solvers. So I think it's an important area to focus, but all of these, there's lots of great research being done there. We work in essentially all of these, as I said, and hopefully many of you on the call do. So there's plenty of work ahead of us. And so with that, I will end. Maybe leave some time for questions and discussion and comments, suggestions, thoughts. I'm looking forward to a conversation.
Great. Thanks very much, Josh. That was a really good talk. We have a few questions in the Q&A panel here. Maybe I will start with those and then we can go forward from there. So the first question is from Mr. Mayank Rakesh, and he's asking for multiphase poromechanics. There might be two different discretization schemes which are coupled, which are your finite volume method for the fluid flow problem and the node-based finite element for the mechanical problem. And this may happen on the same mesh. So, because of the geometries, the problem mesh may be unstructured. So does that affect the finite volume solution?
Definitely. And we have some real experts in the room. So this is really great. This is a great question. So yeah, so a focus of this work is we like to do, we like to solve these problems on a single mesh. You know, some people use schemes where they'll do reservoir simulation on one mesh, interpolate, do mechanics on a different mesh, and then interpolate back and forth. First of all, that creates all sorts of artifacts from the interpolation, and the solution scheme is actually slower because you can't converge it nearly as quickly as you can when it's in a sort of a monolithic system. But what that means is we want to do flow and mechanics on the same mesh. And so, for example, here is a mesh for a real field. This is a Gulf of Mexico field. And it's this one happens to be a highly unstructured tetrahedral mesh. So the discretization we would use for the mechanics is a finite element scheme. So standard Galerkin finite element scheme, node-based. So we'd have degrees of freedom at the nodes of all of this mesh. But for the fluid flow, we like to have element-wise mass conservation. And there's for a variety of other reasons, because of the permeability, heterogeneity, and so forth, we like to use finite volume schemes. And so typically we'll have the pressure degree of freedom located at the cell centers. And then the challenge with finite volume schemes is what we call the flux approximation. The most common flux approximation that people use is 2-point flux approximation. Unfortunately, if you use 2-point flux approximation on certain grids, it's not actually a convergent scheme that you will actually, as you refine the mesh, converge to an erroneous solution, and you may get very strong grid effects. Okay, and so this is a fundamental challenge. And so people say kind of, oh, you cannot use finite volume schemes on a grid like this with non-K orthogonal permeabilities. What we do is that we actually use a slightly different scheme. We use mimetic finite differences. And so that type of scheme is similar to a finite volume scheme, but it leads to a consistent and therefore convergent discretization. And so we can actually run on a variety of element types, essentially unstructured grids, using a finite volume type scheme. We have all the properties of a finite volume scheme that we like, but we maintain consistency regardless of the grid geometry. Hopefully that answered the question. I will say actually a big push for us right now is it's very limiting to have to focus on traditional finite element grids, by which I mean always having to use tets or hexes or wedges or pyramids. So actually we're doing a lot of work now on more advanced schemes where we can use arbitrary polyhedral meshes. What's nice about the mimetic scheme is you can actually run on essentially arbitrary polyhedra. And so that handles the flow component. For the mechanics component, though, we want to do finite element like schemes, though, on arbitrary polyhedra. And so that moves us into the space of things like the virtual element method. If you've heard about that, that's where we're pushing. There are other sort of polyhedral finite element method techniques out there. So that's an exciting research space.
So the next question is from Tao Jin, and he's asking you, as university educators, when we develop or design the course curriculum, how could we better prepare our students for this modern landscape of computational mechanics, which is enhanced by parallel computing techniques?
Well, Tao, it's good to hear from you. That's a great question. I do think it is worth revisiting the curriculum that's provided to students and making sure, I mean, no one, at the end of the day, how can I put this? It has gotten to the point where no individual can write a computer code on their own from start to end and take advantage of a huge supercomputer. You know, it's just simply too much work. You know, there's just too many complexities of like writing a really scalable linear solver. You know, in the 80s, 70s, I think one person could have such a good understanding of all the algorithms, they could write a single Fortran code from start to finish and be able to do that. That is no longer the case. But I do think we want to make sure that students have a really good understanding of, at a high level, all the pieces that go into that. And so, for example, I think in existing curricula, people get really strong preparation in solid mechanics and fluid mechanics. That's great. And you know, whatever your field is, in the fundamental governing physics, they get really good preparation in numerical methods and discretizations. Depending on the school, I think the preparation in linear solvers can be a little weak. So I would spend a little time just talking about the basics of knowing the difference between a direct solver and iterative solver. What is a preconditioner? You know, what really impacts performance? Not at a deep level, but at that kind of high level, so that you can have an intelligent conversation. And then parallel computing. Again, I think people should take courses on parallel computing, understand the basics of parallel data partitioning models, communication bottlenecks, fundamental understanding of maybe CPUs and GPUs and why they're different. Obviously, to go into any depth, you need a lot more than that, but at least a high level language that you can converse intelligently with experts and deep experts in that field, I think is really important.
Okay, so we have one more question here, and that asks you if considering multiple fluids adds much to the geomechanical response in comparison with just a single phase flow, especially when considering the huge burden that you have on the computation. So is the physics, I guess, to summarize that question, is multi-phase fluid flow really important from a physical standpoint, or it's it's adding too much to your computational cost without really giving much by way of significant difference in the results?
So that's an excellent question. Obviously, it's context dependent. You know, so there are certainly situations where a single fluid approximation is more than enough, given all the uncertainties about subsurface response and so forth. But for example, in CO2, in the two examples maybe I've shown, in CO2 storage, the dynamics of the CO2 and its compressibility are very important because it dramatically impacts the fluid pressure distribution, which dramatically impacts the pore pressure response. And similarly, if there was fracturing and you've got two fluids migrating within fractures, that can dramatically impact the pressure, which impacts the aperture, which impacts the permeability. You know, so they're very tightly, they interact very closely. So let's say from a physical point of view, there are many situations in which we need to model both, and it's inescapable to model multiple fluids and the geomechanics. Then a separate question from that is, when we discretize, how tightly do we need to couple though the governing equations? Can we, for example, use leapfrog in time, where we just like solve for a pressure field and fluid field at one time step, keeping the displacements fixed. Then we solve for that pressure. Then we solve a mechanics only problem, just imposing the fluid pressures, and iterate like that. That would be what we call kind of a loosely coupled scheme. What I showed today is the other end, when we say, no, everything has to be tightly coupled together at time step n, and we have to solve all the governing equations and satisfy them simultaneously. And there is a spectrum of in between there of different levels of coupling. And I will just say that depending on the circumstance, you need sometimes that iterative coupling is enough, and there's many circumstances where it is not enough. And our viewpoint is we want to be able to enable people to solve the fully coupled system, to run the simulation, and then also to run an uncoupled approximation and check if the two results look the same. If they look the same, then you can have real confidence that you can run the uncoupled simulation and get good results. Unfortunately, today, people don't really have the capabilities to run the coupled systems, so they often just assume that the uncoupled model is good enough. And we have many examples where you actually get pretty substantial deviations in response because you're missing some important elements of that coupling. So sorry, it's a long-winded response. It's very circumstance dependent, but I will say that there are circumstances which you really do want to capture in nitty-gritty detail that level of coupling.
So we have one more question, which is asking you if you're familiar with any open source code that can model CO2 injection induced seismic wave propagation in a faulted aquifer system. So that's a very specific problem that they're trying to model. So I guess, let me rephrase that question. Can they use geosecs to do that? Maybe that's a more, question that is suited to you.
Yeah. Okay. Today, today you cannot use GeoX to do it. Come back a year from now, and I think you will be able to. So we have a collaboration with some folks at INRIA, which is the French National Laboratory. They've been working on putting wave propagation solvers into GeoX. They currently have a low order wave propagation solver, which is just like the easiest thing to do, but it's overly diffusive. So they're going to go to a high order spec-fem type solver. And so I will say, on our strategic roadmap, one of our goals is that currently in the industry, seismic imaging, which relies on seismic wave propagation, and also induced seismicity questions and all those are kind of just separate codes. They're handled separately. And then there's like reservoir simulation codes, and the two just never really meet in the middle, or they meet in the middle in really clunky ways. And we would like to be able to have kind of one code framework where we can begin to do things like doing seismic inversion, but then actually updating reservoir properties using production data, and sort of couple the seismic imaging process with the reservoir history matching process. And to do that, it'd be nice to have one code framework to do that. Or if you're doing induced seismicity studies, it would be awesome to be able to model fluid injection, fault reactivation. And so you model the fault slip, and then you say, okay, now I want to propagate this energy as a wave away from the fault and see what the geophones at the surface might actually detect in terms of microseismic or seismic response. And so a long-term vision for us is to be able to do all these together, but right now it's too preliminary for me to recommend it. In terms of, there are certainly open source wave propagation codes out there. There's things like DeVito, and if you give me a little bit, I could think of some others. So those would probably be where I would recommend starting. They're really designed for this problem. They're great. But check back in with us in a year, and we can have a richer conversation.
Okay, so are there any other questions from either the audience or the panelist? Okay, looks like we have one more. Do these geomechanic coupling methods apply to well test interpretation?
Yes. Well, let me say yes and no. So one of my interests is actually well test interpretation. What's really powerful about well test interpretation is that it's data driven. Oftentimes you're just using the gauge data from the well, and it's extremely fast. You don't need a supercomputer to do well test interpretation, and so a lot of day-to-day operation is really just using very simple well tests. It's a really powerful technique. Okay. However, the challenge with well test interpretation is more often than not, you begin with a conceptual model to interpret the data. And so, for example, you say, well, let me see if this is a radial flow configuration, and we check, it's not quite right. Let me assume it's fault bounded. That doesn't seem to quite match the data. Maybe it's fault bounded with a vertical fracture. Oh, that starts to match the data. Well test interpretation, a lot of it is really kind of trying to develop these analytical conceptual models to fit the data. But for example, there are many situations where the analytical models just don't cover the space of response. So for example, in a reservoir CO2 field, we often do what's called above zone monitoring, where we put a pressure gauge in an aquifer well above the reservoir, where we don't expect any fluid to migrate. But because of the inflation of the reservoir and the far field deformation, we will often actually see a pressure increase or possibly a pressure decrease at a gauge. And so then all of a sudden the question is, there's pressure increasing at the well. Is that because there's a fracture there and fluid has migrated up to that gauge? Or is it because we just had this gentle inflation of the reservoir and we kind of bent the upper aquifer and we increased the fluid pressure? And so I think having this kind of back and forth between well test interpretation and simulation tools is really important. So hopefully that answers your question. Yeah.
Thanks, Josh. So we have another question here, again, Tao here, and he's asking, when we introduce complex discretization schemes into the simulations, and this is a question that is also close to my heart. For example, if you have embedded strong discontinuities, how would it impact your preconditioning process? So I would also like to add a couple of more things here. Let's say you embed your discontinuities in other ways, like extended finite element methods, or if you're using, let's say, phase field models with adaptive refinement, etc. So what's your take on that?
Absolutely. Okay, so Tal and Chandra, we can certainly have a very detailed conversation about this for those specific cases, but let me give you the audience the rough answer. So that those methods introduce, I would say, two things. The first is that, for example, we may have additional degrees of freedom, so in the embedded methods, for example, I may have displacements U, which live at the nodes of the finite element mesh, but I will have additional displacements, which are actually live on the enriched cuts. So they live kind of in the cell center, loosely speaking, okay? So we have degrees of freedom that live in two different places. And then, yeah, similarly for it's similar for XFEM, except now it's kind of all nodal. The thing what we would do is that when we do in our multi-grid solver, then all of a sudden this U block, you think of it, it may actually have its own structure to it, that we may say that that displacement field can be further partitioned into displacements at the node and displacements at the cell center or on the enriched cuts. And we may, for example, in our first level of reduction, make a choice to actually eliminate the cell cut degrees of freedom to create a reduced problem that only features the nodal degrees of freedom. And for example, we have people, Tal, Matteo Cassini, he's currently working on this. What's a good multi-grid reduction preconditioner for, EFEM or enhanced assumed strain type method. And that's kind of precisely the logic is because of the algebraic structure, it makes sense to eliminate the enrichments to come up with a reduced problem, which is essentially a continuous problem for preconditioning purposes only, and then continue this multi-grid hierarchy as we've drawn it here. For XFEM, I think you could do similar things. The challenge with XFEM and EFEM is when you get very small cuts, you can get really ill-conditioned systems. And so we would, there are other challenges with XFEM in terms of the preconditioner that need to be addressed related to the small cut problem. But yeah, I mean, like this is not an automatic recipe, but this would be the same framework we would use, but we would modify, we'd have more levels, different smoothers, different restriction and prolongation operations to address those types of problems.
And what's your take on the phase field methods with like, adaptive refinement near the crack tips, etc.?
So phase field, well, it depends on how you want to solve it. And I'm not a phase field expert, but my understanding is that so you have the displacement field and then you have the damage field. So those are your two coupled fields. And some people will solve them using kind of like a time staggered scheme where you solve mechanics assuming the phase field split and then update the phase field and vice versa. Or the coupled way would be you want to simultaneously update the displacement field and the phase field. When you're in that space, then you would have a coupled problem. So imagine here, I define S to be the displacements and P to be the phase field. We would do a similar sort of reduction. And so I would have to think a little bit about what would be appropriate, which one to reduce first and what would be appropriate smoothers. But again, we would think about how could we eliminate, if you're familiar with Shor complement reduction, this is kind of the idea that formally I can take a coupled problem, algebraically eliminate one field to write a new problem expressed only in terms of a primary variable. And that's what we're mimicking here, but we don't want to do exact Shor complement reduction because we would end up with a fully dense operator. We want to do what we call sparse Shor complement reduction. And so with phase field, I would have to think a little bit about how could we eliminate one of those fields to write a problem that's approximately equal to a single field problem that does a good job mimicking the coupled problem. That's kind of the general logic that we go through. And we'd have to talk about what would be a good strategy to do that. But I think we could do that algebraically and it's certainly easy to experiment using this strategy.
Okay. So there's another question here, which is asking you the scope of mesh-free methods in subsurface Earth systems.
That's a good question because I was thinking about that the other day. I can let me give you the place where it's maybe limited and then the place where it could be really impactful. The limiting place is that, and I'm not a mesh-free expert, but this is my take on it. The trouble in the subsurface is we have very heterogeneous problems. Our properties often look like this field here where we got this Gaussian, multi-Gaussian geostatistical field. It's very, very heterogeneous. And so your mesh-free method needs some way, I imagine, to be able to construct Green's functions or, the boundary integrals for a domain that's not homogeneous, and maybe there are ways to do that. Most of the mesh-free methods I'm aware of are well, let me take that back. Sorry. I was thinking a little bit of boundary element methods, but there are mesh-free methods. It's a big space of methods. But the first challenge would be to address the heterogeneity. So that's the first thing. But I never ever like to say that a method is not useful because someone's going to come along and say to continuously demonstrate how it can be useful. And so I would say that I think there is some scope. It has not had much penetration into day-to-day practice. But it is very true that a lot of our hiccups come with mesh generation. It's very difficult to generate meshes for complex geologic structures. And so the mesh-free methods, if you can relieve some of that meshing burden, I think they could be very powerful. So let me put that as my answer. Yeah. I shouldn't say more because I'm really not a mesh-free expert and I don't want to say something silly. Yeah.
Well, I personally have a couple of other questions, but I will wait if someone else from the audience has a question.
Yeah, Chandra, may I pose my question
Yes,
instead
please.
of typing it?
Yes, please.
Okay. Okay. This is Antonio Rodriguez. Thanks for a very nice talk. And I have a two-part question about preconditioners. First part is what is a fixed stress preconditioner? More specifically, what does fixed stress mean? And second part is, what do you mean by naive preconditioner? Are you thinking of simply diagonal Jacobi preconditioners, or are you also including, let's say, incomplete Cholesky factorizations?
Okay, two excellent questions. Sorry, unfortunately, I don't have good backup slides, so my explanation of fixed stress may be a little a little tortured, but I can send you a reference which will very precisely define it. So in the coupled, okay, so we have this coupled system of governing equations, okay? And you can see here in the mass balance equation, we have this porosity term, okay, which depends on the volumetric strain, okay? And so when I linearize this term has an explicit dependence basically on the displacement field, okay? When we construct the preconditioner though, like I said, we would like to be able to, for example, construct a reduced problem where we actually eliminate the dependence on the displacement field, okay? And so one strategy to do that is to make an assumption that over the time increment, the stress is fixed. What that does is that introduces a particular relationship between the porosity change and the pore pressure. And the coefficient here is slightly different. It involves b squared over the drain bulk modulus. But we can actually eliminate the volumetric strain completely. And so this fixed stress approximation, it's an approximation of the porosity relationship. It's incorrect, but we don't care that it's incorrect because we only use it for preconditioning purposes. And you can actually show from an eigenvalue analysis that it actually leads to what we call a spectrally equivalent approximation. So the point is that making this simple assumption, we actually uncouple the problem for preconditioning purposes. So we highly simplify the preconditioner, but in fact, we can show that you maintain good control of the eigenvalues, and so you get this flat behavior. This naive preconditioner is not actually that naive. It's actually an algebraic multigrid preconditioner where we apply algebraic multigrid to the displacement block, algebraic multigrid to the pressure block, and we use a block triangular, upper triangular preconditioning process. It is far from naive. It's actually quite sophisticated. The thing that it's missing is actually an intelligent knowledge of that coupling, that subtle detail about that porosity relationship is the sole thing that's actually explaining the going from here to here, if that makes sense.
Yes, makes a lot of sense. Thanks a lot.
Yeah. I will happily, we have a paper where we describe in nitty-gritty detail precisely what we mean by it though, and I can certainly forward that to you.
Okay, any further questions from the audience? Okay, if not, I have a couple of questions, Josh. So first, what can geosecs do today? What are its strengths? and what are the opportunities from a computational methods development perspective? And I'll be selfish here, and I'll ask you only about solid mechanics, but of course you can elaborate on, other areas as well.
Yeah. Okay. Well, I'm gonna go off book here. And so let me see if I can share my screen again. Can you all see my screen and my web browser?
Yes, we can.
Sorry. So, okay. Well, so for folks who are interested, please go to geosx.org. And we have various, the Zoom bar is getting in my way, so I have a little difficulty seeing. Yeah, so we have various resources here. If you want to visit the source code, you can come to GitHub and you can actually, download the source, submit issues, all sorts of stuff. So direct access to the source. I think the most useful thing for many people will be to come to the documentation. Here we've got things like tutorials, so for example, in our tutorials, we talk about simple things like doing multiphase flow, CO2 injection, modeling an elastic beam. We've got some Terzaghis pore elastic problem. We have a hydraulic fracturing problem. Very simple. These are all very small, very simple problems because most people want to run these on their laptops. So, but this would be the place to start. In terms of capabilities, then we have the key capabilities, I would say, are the following. We have a solid mechanics solver, which does small strain elasticity and plasticity. And it does finite strain elasticity, but currently it just uses a hypoelastic update. We do not yet really have a like a total Lagrangian kind of hyperelastic finite deformation solver. So that's a limitation that, if someone's really interested in finite deformation mechanics, please jump in. We would totally support that. In terms of fluid flow, we have very sophisticated flow modeling capability. We have compositional flow and multiphase flow. So I think our capabilities there are very mature. The things that we're working on right now are thermomechanics. That's not really in the code yet, and that's an area for growth. And then we have various couplings between those. So you couple solid mechanics to flow, and you get the solid compositional solver and all sorts of stuff. Okay, in terms of places for growth, we're doing a lot of work right now on faults and fractures, but that's a really rich field. Contact mechanics, slip, embedded discretization methods, XFEM, EFEM, these sorts of things. Lots of interesting work, I think, that could go there. In recent years, we haven't done much work on hydraulic fracturing, but we've kind of maintained a little bit of an activity there. And we have a basic solver. The key challenge with that solver, I will say, is the appropriate treatment of the tip, the propagation criteria, and capturing the near field behavior of the pressure field and the deformation field in the tip. Emmanuel is on the call, so I'm looking at him. There's lots of interesting research there on improving the representation of the behavior near the tip. I think that's the dominant thing. We have a relatively naive method, and I think that could be dramatically improved. We've got some folks working on phase field, which is an interesting growth area, and also phase field coupling. The challenge with phase field is it's very computationally expensive because you have to resolve the entire fracture at the phase field. You have to, at the phase field resolution, you have to have 3 or 4 elements across the entire phase field. And so for field scale problems, it's really impractical, I think, to directly just use phase field using realistic properties. But one option we're looking at would actually be to use a multi-scale method where we modeled at large scale the fracture using embedded methods like XFEM and EFEM, but only at the propagating fracture front. we could potentially use a phase field on a much smaller domain and some sort of intelligent coupling between that micro scale domain and the macro scale problem. That's a challenge problem. Who knows if it'll work? But that's an interesting area for exploration. So I could probably go on for 20 minutes with other ideas, but I think faults and fractures, broadly speaking, all the behavior around that is challenging for us, and that's a focus area for us right now.
Yeah, thanks, Josh. I think I will stop with the questions. Anyone else in the audience? Okay, so I think we don't have any further questions. Thanks once again. It was really a pleasure to see you again, and also to listen to you speak. And it's good to see how far GeoSex has come, and hopefully we'll get to work on it again and contribute in some of the focus areas that you have suggested. Okay, thank you, Josh. I think. Yeah, I think we'd like to stay in touch, and hopefully once the pandemic ends, we'll get to meet in person.
Yeah, absolutely. Well, thanks again for inviting me. Anyone who's wants to get in touch, please just email me. I'll try to get back ASAP with papers, references, links. We enjoy collaboration, so please be in touch. Okay.
Thank you, Josh. Bye.
Bye.